4 of you responded. So how's everyone doing today? Mostly ups and in the middles. Wednesday is the rough part of the week. Especially for like weeks like this, to me, have felt like forever. But this week has been going on for so long for some reason. Yeah. Long week. Couple things. I need to open the homework for 1 point just covered. And we have a lab on Friday, so we'll be in that lab room downstairs. It's 80, I think it is. The one that we were in last time, I think there. Yeah, the lab is very, very, very important on Friday. Right? All the labs from here on out are very important because your next 2 tests are lab tests. So all the material that you're learning for the test is what you're going to be doing in the labs. We'll learn like the math, the basic stuff in here, and then you'll be able to apply it in Excel. Questions for me? Anything else? Just a note, if you haven't taken test 2 yet, you need to get that taken this week. Office hours tomorrow morning are whatever time you come in until 12:30. Otherwise, we can arrange for other times. So if you haven't taken it, you need to get it taken by the end of this week. Otherwise, I will put it. All right. So over the past couple of lectures, we've been reviewing linear equations, graphing them, finding the solutions, all sorts of stuff. And now we're talking about solving multiple linear equations at the same time. Systems of linear equations. So we'll look at a couple of different ways. First, we want to consider what are some like situations where we would need a system of linear equations. So for example, if 2 shirts and 2 pants cost $44 and 1 shirt and 3 pants cost $46, I'm going to find how much do shirts cost, how much do pants cost, given this in. So maybe I let X be the price of the shirt, Y be the price of pants, and I can set up my system of linear equations like this, and then I could solve both of these in some way. For example, if a shirt costs $0 and pants cost $22, this first equation would be satisfied, but the second equation would not be satisfied. You'll have to see. In college algebra and in calculus, do systems of linear equations. So all of you at some point should have seen solutions of systems of linear equations. So we'll revamp that idea and then do it in a couple of different ways. In general, the definition of a system of linear equations is just if I have 2 linear equations derived in what we call standard or general form. Basically, that just means we're lining up our x variables, we line up our y values, and then we put the solutions to the equations on the right-hand side. They're always written out. This is how we're dealing with them. A, B, C, D, H, and K, all of these are real numbers. And a pair of numbers, x naught and y naught, give you the solution. We call that the solution. There are a couple of different ways that we can find these solutions. One of the easiest ways is graphing them. For instance, if I rewrite this in y equals mx plus b, so that's going to be y equals negative x plus 22. It's going to be y equals negative 1/3 x plus 46 over 3. Then I could graph these 2 equations. Maybe this one looks something like this. This one looks over 3 is approximately like this. And so I'll have a solution point right there. Right where the equations overlap is a solution point. So that's one of the most basic examples. A lot of the problems we do, unfortunately, are not going to be able to be solved by graphing, at least not by hand. A lot of them we could graph in Excel. That was something that was done quite often in college algebra, Excel labs, as you graph two equations and you find their intersection. For instance, this right here is the solution set of a paragraph. If they have the same slope, but not the same intersect, there's no solution. They're parallel. Same slope, different intersect. That means there's no solution. And if they intersect everywhere, there's infinitely many solutions. This is same slope and same intersect. That's infinite. Most of the time, we're going to see this case. This is almost always just different slope. They can have the same or different intercepts. More than likely, they're going to have different intercepts as well, because otherwise their intersection point would just be the intercept right there. Give an example here. To solve each of the following systems by graphing, then state if consistent or inconsistent. Consistent just means like if it has a solution pair right here, inconsistent is no solution pair. The definition right here. At one point, they're consistent. At no point, they're independent. If they're everywhere, they're consistent and dependent. Inconsistent is just when they're parallel. This says solve both equations for y. Here I'm going to move this 3x over. So I get 2y equals negative 3x plus 4. And then I just divide by 2. So y equals negative 3 halves x. Other equation, I move the 2x over. So y equals negative 2x plus 9. And that's my whole equation. Then I can graph them. Graph them here in Excel already for you. And it gives you your solution point. My solution point is 14, negative 19. For this top line, which equation is this top line graphing? Which of these two equations is the top? Yeah, this one, because the intercept is 9. Negative 2, 9. This means this one is negative 3 halves x plus 2. And then, yeah, when you graph in Excel, it gives you your solution point. We did that in the first Excel lab. We had lines that were overlapping. A couple more examples. For instance, if we have 3x plus y equals 8, 6x plus y equals negative 4. One thing that I noticed about this, what happens, again, if you can't see something, let me know, because I don't have a preview of the screen anymore. So like if I'm looking at this, I can't see. If I multiply this top equation by 2, I get 6x plus 2y equals 16. Bottom one says 6x plus 2y equals negative 4. Is this possible? The same equation can't equal two different things if variables are the same. So there's no solution. We could also graph these if we wanted to. We could solve each equation for y as well. I get y equals negative 3x plus 8, or y equals negative 3x minus 2. So these are two different equations. They have the same slope, but a different intercept. That means there's no solution. Then right here, well, I notice that if I multiply this top equation by 2, get 2x plus 8y equals 12, and 2x plus 8y equals 12. These are the same equation, there's infinite solutions. Again, if I wanted to solve each of these in terms of slope-intercept form, this one would be negative, or y equals negative 1 for x plus 3 halves, and also y equals negative 1 for x. So infinite solution. Again, this means that they're consistent with each other, consistent, and dependent. No solution means they're inconsistent. That means that they can't have the same variables. So, kind of have a theorem that lists this out. A linear system like this must have either exactly one solution, in which case we say it's consistent and independent, no solution, which means it's inconsistent, or infinitely many solutions, which is consistent and independent. And just so we know on a case-by-case basis, exactly one solution, different slope, and any intercept. No solution means same slope, different intercept. Infinitely many solutions, same slope, same intercept, or just in general, they're the same equation. So those are the different cases that you're looking for. Any questions so far? Other methods of solving them are doing it computationally, right? So there's the substitution method and the elimination method, which is what you learned in college algebra or business calculus as well, right? So it's where we multiply the equations or solve the equations for a variable and do some really normal. For example, if I have this one, it says it's solved using substitution. Substitution means I solve one of the equations for a variable, plug that into the other equation. Which of these looks easier to solve for one of the variables? The top one, right? Because I have y by itself. I can just move the 2x over. Get y equals negative 2x plus 5. I'm going to plug this into the bottom equation. Negative 4 times negative 2x plus 5. Oh, that's x. My bad. Negative 4x plus 6 times negative 2x plus 5 equals 12. So this is just an equation in one variable, and I can solve for the variable. Negative 4x minus 12x plus 30 equals 12. Negative 16x equals negative 18, and x equals divide over by 2. I get 9 over 8. And I can take this value of x equals 9 over 8 and plug it back in to my top equation. So 2 times 9 over 8 plus y equals 5. So 18 over 8 plus y equals 5. Y equals 5 minus 18, 8. Same thing, 8. 8 minus 18 over 8 equals 22 over 8, which is 11 over. My solution pair is 9, 8, 11 over. I can plug these solution pairs into my systems of equations, and they should both be satisfied. Again, this process was solve one of the equations for a variable, plug that in to the next other equation, and then plug the solution for the other variable back up. That's all there is. I also didn't even need to do all this. I could have just gone straight to the source right there. But that's basically exactly what I did. So either way, it's good. Just maybe a little less rearranging or something. Any questions about the substitution? We can also use elimination. So we can multiply the equations by something such that one of the variables cancels out. Here, I'll multiply this bottom equation by 7. Multiply this top equation by 2. So I get 6x minus 4y equals 20. Remember, when I multiply an entire equation, I have to multiply every single part. So that's both sides. Multiply by 7, I get 8x plus 14y equals 5x. Is 252. Okay. And then I can add these together. I notice that when I add these together, my y's cancel out. So I add up my x values. This is 34x equals 272. Then I can divide both sides. And x equals, is 8. I can then plug this value into either of my equations. I know that the value of x has to be 8. So which equation? Bottom one? Sure. So 4 times my x value, 8, plus 2y equals 36. 32 plus 2y equals 6. 2y equals 4. So y equals. My solution pair is 8, 2. I went kind of quickly through that algebra, but it's just basic arithmetic. Just plugging in values, subtracting all. Any questions about this? Next, it says to solve this system of equations using any method. Which of the two methods seems easier, substitution or elimination? Elimination, because if I add these equations just straight up, the y's already canceled. I'm going to add them. I get 2/3 plus 1/2 x equals negative 2 minus 1/3. I can then just do addition of fractions. So this is 4/6 plus 3/6 is 7/6x equals negative 6/3, so negative 7/3. So x equals negative 7/3 times 7. 7's cancel, so I get negative 6/3 is negative 2. Again, if you want to, you could just. So now that I have a value of x, I can plug this into either one of my things. I'm going to plug this into this one because x is 2 or negative 2. Divide that by half, I get negative 1. Not too bad. 1 half times negative 2 minus 1/3 y equals minus 1/3. Negative 1 minus 1/3 y equals third. I'll add 1 to both sides, so I get negative 1/3 y equals negative 1/3 plus 1 is 2/3. So y is 2/3 times 3, negative 2. So I also get that y is negative 2. My solution set is negative 2 and negative 2. Again, pretty straightforward here. It's just remembering what all you have to do because there's a good amount of steps I have to do. Substitution, I solve one of the equations for a value of a variable, plug that into the other, solve, and then plug back. Elimination, in my opinion, is a good bit easier. I just multiply the equations to get one variable by itself, and then plug that value back into either equation. What happens in the elimination process when a system either has no solution or infinitely many solutions? So consider this one right here, this system. If I multiply both of them by negative, or if I multiply this one by negative 2, I'm going to get negative 12x plus 6y equals 7, or I get negative 12x plus 6y equals negative 4. So there's no solution. Or if I were to multiply and add, I get 0 equals 11. So not looking too good for us. A contradiction in this answer here, for instance, 0 equals 11 is not true. That's a contradiction. It means there's no solution. However, something that is always true is infinitely many solutions. These the equations were equal to each other. So in this case right here, if I were to multiply or divide this entire thing by 2, or by negative 2, I get 3x minus 3 halves y equals 6. These are the same equation, so I get infinitely many solutions. With lines that coincide, I can let x equal k, where k is any real number, and then solve the equation for y. In this example, I get y equals 2k minus 4. So that means any pair of k and 2k minus 4 solves the solution. So k can be 5, negative 20, pi. It could be whatever you want. As long as k and 2k minus 4 is the solution set, that will be your solution. So in this case, what they did is they solved each equation for y equals x plus 4. That form was y equals 2x minus 4. I solved that. And I just let x equal k, and then my solution pair. K here is what we call a parameter. So it's something that changes over time, or just in general, it's something that I can like slide across the scale or something. For example, consider some particular solutions. If this is my solution set right here, this k and 2k minus 4, I can plug in like negative 1, 2, 2.8, whatever. And all of these are going to satisfy both of these equations up here. Any questions about this? This kind of seems a little abstract until we see it as an example. So when we look at an example, we can do this, what we call parameterization. We'll look at some applications, specifically with supply and demand. Class, of course, applications. Suppose that the supply and demand for printed baseball caps are given by these two equations. So I have a supply equation given price and a demand equation given. So it says find the supply and demand if baseball caps are $4 each. So I just plug in 4 equals 0.42 plus 3, 2 and 4 equals negative 1.9 q plus. I'm solving for whatever q is here. So I'm just looking for the value of q. This is a little gross with all of these like decimals and everything, but this is doable. I'll multiply this top equation by 1.9, bottom equation by 0.4. So let's 4 times 1.9 is 7.6, and that equals 0.76 q plus q 6.08. Then is 0.16 equals negative 0.76 q plus 0.18 is 6.8. We add these together. Yeah. And I get 7.76 equals 12.88. That's a contradiction value. It says discuss the stability of baseball cap market price. Is inconsistent. Yeah, both of these can't be true. These are different equations. So unstable, I suppose. I'll take a look at this. Yeah, both of these can't be true at the same time. I'm wondering if there might be a typo here. I need to find it for a different price too, but these can't be both true for any price. So I think there has to be some sort of typo here with something. I'm not. Because if the price is the same for both of these, they cannot be true. So I'll check this. I'll check B. It says find the equilibrium price and the quantity. So we're solving for P and Q here. What I'm going to do is I'm going to rewrite these so that I get AP plus BQ some value EQ equals that. So just rewriting these in standard form. So I'll get 0.4 Q minus P equals negative 3.2 and negative 1.9. Add these together. Okay. That'll begin at 0.4 minus P2 and 1.9 plus P. Adding these, the 2, 3 equals 2 is 8, 3, 3, 3, 6. So we're selling 6 of them, and I can plug this into either one of my equations to get that. So E equals, maybe I'll do this first one, 0.4 times Q6. Q equals 2, which is 5.6. So the equilibrium price, and I'll write it up here, or the equilibrium point is selling 6 hats at $5.6 a piece. 6 hats, $5.6. So that means both of these are unstable. I guess that's what that's. Right, because both of these come out to inconsistent solutions. This is the only solution that's consistent. Like if I plug in 5.6, then I'll get an equation or a stable solution. So unstable because it's not. So when we have a system of equations that's modeling supply and demand, the only stable point is the equilibrium point. Otherwise, we get inconsistent. Example 5 just says I don't have to solve, I just have to define variables in the problem. For a particular event, 651 tickets were sold for $1,622. The students paid $2 per ticket and non-students paid $4 per ticket. How many were sold? Well, I know that the amount of students plus the amount of non-student tickets sold has to be 651 total. Also know that students paid $2 and non-students paid $4, and the total price was $1,620. So this equation gives total tickets. This gives total price. S equals student and equals. So again, if I'm given this information, I'm told how many total tickets were sold and what the price of those was given the total of, or given the price of each individual ticket, then I can set up this system of equations and from here determine how many students attended and how many non-students attended. So again, I'm given a piece of information. There's 651 tickets sold. I know that has to be the sum of student and non-student. There's no other way, right? The only way is for me to have both student and non. And there's no multiples of each of them. Like I don't double the amount of student tickets. It's just all the student tickets I sold and all the non-student tickets I sold. Then 2 times S comes from the fact that student tickets are $2 each. 4 times N, non-students, $4 each. So this gives the price. This is the dollars for student tickets, dollars for non-student tickets, total dollar. And again, I can just solve this. And then just a couple of more examples here. And the next example, the next lecture is going to be Max t-shirts sold. Oh, and it says for all the following examples, I just set up the system I don't have to solve. Oh, this one it says how many features sold. Okay, so where do you solve these? We sold 36 t-shirts in one day. They are short sleeve and long sleeve. So I know that the total amount of shirts sold is 36. If a short sleeve is $12, and a long sleeve is $18, my total value was 522. And now I can just solve these. Almost always, systems like this are going to be substitution. Substitute for either variable. Let me pick maybe S, I don't know. S equals 36 minus L. I'll plug that in this one. And I get that 12 times 36 minus L plus 18L by 22. 12 times 36 is 42 minus 12L. 18L equals 522. 6L is 90. So L equals 50. So I'm able to see how many of my long sleeve shirts I sold by solving S in terms of L, plugging that into my other equation, and then solving for L. Because L is 15, S equals 36 minus 15, which is 19. Of 21. My solution pair of short sleeves and long sleeves is 21 short sleeves, 15 long sleeves. Do the same for the next few examples. The landscaping company placed 2 orders with the nursery. First order was 13 bushes and 4 trees, which was $487. Next one was 6 bushes and 2 trees, $232. So we want to see what's the price of these. In this example, we're not given we're solving for the cost of each tree, or the amount of, the cost of each tree, and we're given the amounts. Which of the 2 methods seems the easiest to solve? Elimination or substitution? Elimination, right? If I multiply this bottom equation by -2, then my t's will cancel out. So multiply by -2, I get 13 plus b equals 7, -12b minus 4 equals -64. And these b equals 23. And I've already got one of my values here. Very convenient. That's just my view. Then I can plug this into either one of my equations, which we want to pick. Bottom. That makes sense. It's a smaller number. We like doing this. So 6 times 23 plus 2t equals 232. Times 23 is 138. Equals 2. 2t equals 2 minus 1, 8. So t equals 37. So now my solution set, which is dollar per bush and dollars per tree, is the bush was, what did I say, $23, and the tree was $47. Again, pretty straightforward. We're setting up our system and then picking a solution. It says 98 passengers rode in a train from Boston to Denver. Tickets for regular coach seats, so regular, cost $120, and sleeper, I know there were 98 people, or $290. A regular is $120. My sleeper is $290. And my total was $19,750. So again, the first equation came from the fact that the regular and the sleeper total to all 98 passengers. And then the cost of regular was 120, the cost of sleeper was 290, and the total cost was 19,750. Should I use elimination or substitution? Substitution. I could solve this first equation for R or S, and then plug that into the bottom. I'm going to solve for R. R equals 98 minus S. The only reason I did that is because 120 is smaller than 290, so I get smaller numbers, but whatever you prefer. So 120 times this value of R, 98 minus S, plus 290S, equals 19,750. 98 is 760 minus S. 90S equals 19,750. 1950 minus 11,760 is 790. 990. 90 minus 120. And then I just divide this by 70. I get S equals 7. And then plug that into this equation. 98 minus 47 is 51. So R equals 50. So my solution set, S and R, amount of sleepers and amount of regular, is 47 sleepers, 51 regular. Basically the exact same thing we did with the up here. We know what the total of the amount for each is. We know what their costs add up to, so we can solve there. Since Tim Duncan scored 32.8 game without scoring any 3-point shots, and he scored 21 times, made several free throws, so that's worth 1 point, and he took shots in the paint, 2 points. How many free throws did he make, and how many 2? So we're looking for our free throws plus our, I'll just call them the field goals, so G. And he scored 21 times. The free throws are worth 1. Field goals are worth 2. His total points were 32. So I can solve this. I can either solve by substitution or by elimination. This one's actually going to be easier to solve by elimination because these right here are the same. So if I just subtract the equations, I'll subtract this way, but it doesn't matter. 2G minus G is G. 32 minus 21 is 11. So you took 11 of these 2-point shots. 11 2-pointers. And the rest were these 3 shots. 10 of those. 21 minus 11. And so overall, this was a pretty simple example to put together. It was just kind of labeling them and everything. This was total shots. This was total points. Every time we do a problem like this, it'll give me 2 totals. For instance, up here, it gave me total shirts and total value. So I could set the equations up like this. This one gave me, this one didn't necessarily, like it gave me 2 totals, but it wasn't like total bushes and total trees or anything like that. It was some amount plus some amount equals this value, some amount plus some amount equals this value, and it's all there. This one was total passengers and total cost. This one was total shots and total points. That's all I have for y'all today. Remember on Friday, we will be in the lab. Make sure you are there. It's a really, really, really important. If you have haven't gotten your graded exam back yet, please come see me to get it. Otherwise, go through.